Hello, my name is Komal Amara,
Hello, my name is Garrett Jackson.
and this is the first prototype, the quarter-scale model of the wind turbine facility. This prototype is not only functional, but has variable speed controls just like the real deal. This prototype showcases the operations of the facility and helps us visualize the methods of the experiment.
The full-scale wind turbine will have water droppers, and as the blade rotates, the leading edge will impact those water drops, and it'll simulate water droplet erosion as seen on real-life wind turbines out in the field. I'll start the demonstration of the speed control. First, I'll turn on the battery pack, and as I rotate the knob on the potentiometer, it'll increase the speed.
When building this prototype, at first we weren't really sure on how the orientation of the leading edge should be aligned respectively to the hub. But after building this prototype, we realized that the leading edge should be aligned to the center of the hub.
Everything on this model is quarter scale, except for the wind turbine blades themselves, because we haven't finalized the airfoil shape or the size of the airfoil quite yet. The purpose of this prototype is to serve as a display or to show a functioning model of what the wind turbine will be. We don't really have good videos, and there's no airfoil on the full-scale wind turbine just yet. There's just a small sample folder, and so this will help us get an idea of what we want to do for the airfoil.
My name is Gruenwald.
I'm Zachary Condes.
And for our prototype, we decided to go with a small-scale 3D printed model of the interior structure of the blade. So this would be that rod going through these 3 extruded airfoils, and that rod is the one you saw in the first prototype that is rotated by the motor. In between each of these airfoil section pieces is a connector that is used for both stability and just getting even spacing between the two. And later on we can modify that spacing depending on how long we want the full blade to be. And to make it look like an actual blade, because this is not very aerodynamic, we would be getting thin polymer sheets or thin aluminum sheets and wrapping them all the way around to encompass the surface and be able to cut through the air and get that erosion testing.
So our big inspiration for this design was for airplane wings rather than a wind turbine blade itself. A is because we want it to be a little more sturdy than a wind turbine blade that tapers off and gets really small near the end, since it has to withstand very fast rotations. And the other reason is because it's lightweight and cheaper since you use less material.
Also trying to, the other option for building it would have been molding complete fiberglass blades, which would be expensive, and we really don't know how to do that, so this option is much better. What we learned from this is, firstly, these sections, although they look small from far away, scaled up, they would be pretty thick and pretty long, which means very heavy and very expensive. So if we were able to thin this down, maybe scale down the model or make it a little shorter, it would make it cheaper, maybe easier to produce, and also we could shell out some of this unnecessary material inside, making it much lighter. Another thing that we learned is after talking with the clients and doing some more brainstorming, we realized that having that one sheet that goes all the way around, after it's eroded, you have to take off that entire sheet and replace it with a new one and then do all your tests like weight and other erosion tests on that sheet. However, that's a waste of a lot of material because this material isn't getting eroded, it's just that leading edge. So our new proposed direction is to basically cut off this front section and instead of having one sheet that goes all the way around, maybe we'll have like half cylinders that encompass the length of the blade that we'll be able to detach and reattach once they get eroded, and then you can throw on a new sample. That way, this material that is on the back side never has to leave. You're just quickly changing out those front sections.
The other thing that we need to figure out is how exactly we're gonna secure each section and each area into the rod itself. We're thinking most likely we're just gonna screw in each section into the rod. And the other thing we need to know about is how to make sure it stays on the rod when it's spinning. So we'll experience a lot of centripetal force trying to pull it off the rod. So most likely we're just gonna go with an end cap or some other system to make sure that the blades do not come off of the rod. The other thing is more internal support between the blades to ensure that they don't attach and that they are really stable.
Hello, my name is Garrett Jackson,
My name's Orion Levasheff.
and this is our prototype for the senior design project. Our task was to design a full-scale section that would easily be able to be used as a visual cue for the profile of the blade. The profile that we used went by the name of GOE 460, and that supplied zero lift as the blade rotated across the hub.
So the purpose of this particular prototype was to show the dimensions of the cross-sectional airfoil, and we will be making like changes in the future, such as shortening the back to reduce drag and anything else.
And then increasing the front leading edge to have more surface area for the water droplets mentioned in the previous prototypes to hit and cause more erosion.
So for now, with this particular prototype, it's made out of foam, as you can see, but going forward, we're going to be using more stronger materials, which is going to end up being heavier, like previous subgroups mentioned. And to get rid of the weight, we're going to be cutting holes in each section to reduce the weight but still maintain structural integrity, and make it more stable by moving the center of gravity to the rod.